In this discussion video, we'll be talking about inverse trig functions. So recall that if I have a trig function like cosine, I plug in some angle theta into it. So I plug in an angle into a trig function, and what I get out, I'm going to call r. That value I get out is a ratio. It's a ratio of side lengths in a triangle. So when we talk about the inverse of this function, which I'll write as cosine, I write this -1, kind of like an exponent, except it's not actually an exponent, it's just notation for inverse trig function. An inverse function is supposed to switch the input and the output. So the output of cosine was r. That's now the input of the inverse function. And the input of cosine was this angle theta. That's now going to be the output of the inverse function. All right, so the problem that we run into is there can be an infinite number of angles that, when we take the cosine of them, give us the exact same ratio. So when we come to talk about the inverse function, if I plug in some ratio, it's going to give us a bunch of potential angles out. And we don't want that, because a function is supposed to just have one output. So we need to restrict the values of theta, so we only get one output in this inverse function. All right, so let's review how we did that. And I'm going to give a little bit more information than what I did in the lecture videos. Okay, so I'm going to make a table here where I keep track of my trig function, like I have the graph of y equals cosine of x drawn, and I have a couple of points labeled. So this point right here is where the angle is pi/2, and at that point, the output of cosine is 0. And when the angle is pi, that's this bottom point of the cosine graph, where the output is -1. So to make this function have an inverse, we need to restrict the domain so it's going to pass the horizontal line test. So the convention is to just let the domain go from starting here, when the input x is 0, all the way up until here, where the input is pi. So our domain restriction that we're going to apply so that this has an inverse is that the angle can only be from 0 to pi, including 0 and including pi. And on that interval, the range, which I'll just denote with r, so this is going to be the range. Remember, the range is the possible y values that we get. The smallest range, smallest y value is -1, and the biggest one is 1. So that's my range. So now let's draw the inverse function graph. This is going to be new from lecture. I didn't actually graph the inverse function in lecture. Okay, so I'm going to draw some axes. In fact, let me draw it like this. And I'm going to plot 1 here, -1 here. And I'm going to start with these. So one of the things that I want to notice is that with the inverse function, the inputs and the outputs are supposed to be switched. So when I talk about this point right here, right now the x-coordinate is 0, the y-coordinate is 1. On the inverse graph, the input and the output are going to be switched. So that means it'll be 1, 0 on the inverse graph, 1, 0. If I do that for another point, this point over here, x-coordinate is pi/2, the y-coordinate is 0. So when I switch them, I'll get a point on the inverse function graph. So I need the y-coordinate to be pi/2, and the x-coordinate to be 0. That's somewhere here. And then finally, if I do that for this point, the x-coordinate there is pi, the y-coordinate there is -1, and I'll switch them when I get to the inverse function graph. The x-coordinate is going to be -1, the y-coordinate is going to be pi. I'll get a point here. And now I'm going to draw in this cosine inverse graph to sort of kind of match, the way that this other original cosine graph was kind of curving. So it'll kind of look like a little flatter here, and then curve like this. And that is the graph of inverse cosine of x. So the domain of this graph, I'll just call it D. The domain is from -1 to +1, and the range, I'll call it R. Smallest y value is 0, and the biggest y value is pi. And notice that when we compare that to the original cosine graph, the domain and the range are switched. And that should happen because the inputs and the outputs are supposed to switch when you talk about going from the function to the inverse and vice versa. Okay, so one final comment I want to make about this is sometimes with inverse functions, we'll see them written as like arc cosine of x. So when you see this, arc cosine just means cosine inverse. All right, so for practice, let's do this with the tangent graph as well. So I've gone ahead and graphed in the tangent graph. This is the one that's got all of these vertical asymptotes. And I've labeled two of them at negative pi over 2 and positive pi over 2. Now let's try to draw the inverse tangent graph. I'm going to draw on some axes, and I want to first have you pause the video for 1 minute. And actually, sorry, before we get into the pause, let me talk about where are we going to restrict this graph. So remember, the convention is for tangent, we restrict it to this middle portion so that it ends up passing the horizontal line test. So our domain restriction goes from negative pi over 2 to pi over 2, but I can't include those endpoints. I have to put parentheses because of these vertical asymptotes. Tangent is undefined at pi over 2 and at negative pi over 2. The range goes from negative infinity to positive infinity. At negative and positive infinity, we always put parentheses because they're not actual numbers we can reach. Alrighty, so now I'm going to have you pause the video for 1 minute to see if you can try to graph the inverse tangent graph. 4, 3, 2, 1, pause it, see if you can draw the inverse tangent graph. Alrighty, so hopefully you did that. Hopefully paused it for about a minute to try to graph the inverse tangent graph. So the first thing that I'll do is notice that in tangent's graph, it had these vertical asymptotes. When that gets switched to the inverse tangent graph, those will now be horizontal asymptotes. So there's going to be a horizontal one at positive pi over 2. And there's going to be a horizontal one at negative pi over 2. One of the graphs on tangents, one of the points on tangent's graph was 0, 0. And when I switch the x and y values, it stays 0, 0. So that's going to be a point on the inverse tangent graph. And now, when I sort of flip all the x values and the y values, inverse tangent's graph looks like it sort of snakes horizontally up like this. And now let's label the domain and the range. The domain is going to be from negative infinity to infinity, and the range from negative pi over 2 to positive pi over 2, parentheses, because I never actually reach those y values. All right, so let's end this video with a practice problem. So this is question number 10a from worksheet 1. I want you to simplify tangent inverse of negative root 3. So I want you to first pause the video for 2 to 3 minutes to try this. 4, 3, 2, 1, pause it, and really try this for 2 to 3 minutes. Alrighty, so hopefully you did that. So you paused it and tried it for about 2 or 3 minutes. It's totally fine if you didn't finish it or if you had questions, but hopefully you got started thinking about what the key ideas might be. So I know that with tangent inverse, let me just rewrite this. I'm going to let tangent inverse of this value. I know that with tangent inverse, with any inverse function, I plug in a ratio, and what I get out is an angle. So I'm going to let this be equal to theta. I get out an angle rather than plugging in. With the original trig functions, I would plug in the angle. Okay, now if I rewrite this in terms of the original trig function, we'd get tangent of theta is equal to negative root 3. So I need to know when that happens. So let's draw our unit circle. So I'll draw some axes, and I'll draw our circle. So tangent is going to be negative in the second quadrant, so somewhere here. Somewhere in the second quadrant, doesn't really matter where I put that dot. And then somewhere in the fourth quadrant, it's also going to be negative. Turns out these points, they're going to be symmetric from each other. I'm going to connect these with the origin, and then drop perpendiculars to the x-axis to make my right triangles. And now I'm going to fill out these values This either comes from if I have the unit circle memorized, or if I use my 30, 60, 90, 45, 45, 90 stuff. So if I want tangent to be equal to negative root 3, remember the unit circle tangent is y over x. To get a value like negative root 3, one way that could happen is if this vertical length was root 3 over 2, and I can see now, oh, this looks like a 30, 60, 90. That would mean that the horizontal length is going to be 1/2. But the horizontal length corresponds to a negative x coordinate, so I'm going to put a negative in front of that 1/2. And the radius, of course, is 1, so the hypotenuse is 1. And then by symmetry, this is root 3 over 2. I should put a negative in front of it, because the y coordinate at this point is negative, and the horizontal length is positive 1/2, because the x coordinate at that point is positive, and the hypotenuse again is 1. And then using my 30, 60, 90 information, this is 60 degrees, this is 60 degrees. So I can see now what the angles in my triangles sort of look like. What I need to remember is that with inverse tangent, remember that the angle is restricted to be between negative pi over 2, which is here, until pi over 2. So we're limiting the angle to be in this range, which means we have to be talking about this point. And that angle, I need to write it as an angle between negative pi over 2 and positive pi over 2. So that is going to be negative 60 degrees, or negative pi over 3. It's really important to notice that I can't use 5 pi over 3. Even though 5 pi over 3 is in the exact same spot, if I had just gone in the positive direction, it's not a value between negative pi over 2 and positive pi over 2. So I really have to use negative pi over 3. Alrighty, so we know that our angle theta is negative pi over 3, and that is our answer right there. That is what tangent inverse of negative root 3 is, or if I wanted to, I could have written this as arc tangent of negative root 3 and said that that equals negative pi over 3.